Welcome to my thesis presentation. So, as the title goes, I'll be talking about AI in brain microstructure investigation using clinical diffusion MRI. Now, the clinical diffusion MRI is limited in the study of brain microstructures. So, we will see how AI could be used effectively to mitigate those limitations. So at first, let's talk about the physics of the problem, which is diffusion. This is a very common physical phenomena observed in the liquids. Now, this was observed in the 18th century by Dr. Robert Brown, but this was first mathematically modeled by Einstein in his PhD thesis, where he shows that the diffusion length is directly proportional to the square root of time, given that a particle is diffusing freely. Now, if the particle isn't diffusing freely, there will be a nonlinear relationship with time. And now, as we take a closer look at the brain microstructures, we find these structures with restricting water in different ways. So, based on how different structures restrict the water movement, in theory, we should be able to get different diffusion profiles. As 80% of human brain is water, some form of these distributions are likely to be observed in the brain. So it can be said that diffusion can give us structural information at a at a very cellular level, and it is useful for detecting structural changes by any diseased condition at microscopic level. Now, to do non-invasive diffusion measurements, we need to perform diffusion MRI. And diffusion MRI can be done in these three steps. First, we get the T2 weighted MRI for reference. Then we apply directional diffusion sensitive gradient. And as we apply this directional diffusion sensitive gradient in different directions, we sample the directions on a Q space. This is a spherical space. The samplings on which this is taken, this is termed as Q space. And then finally, the signal that we have for these different samples, this is the signal, we can model those signals on this particular Q space. Now let's look at these steps a bit more in detail. In general, the MR, when we talk about MR, we actually talk about a very powerful magnet, around 60,000 times powerful than the Earth's magnetic field. So when we put a scanning object inside the scanner, we do this to get uniform magnetic field in the subject that we are scanning. Now, now we apply some form of energy pulse in this uniformity to disturb the system, and then we listen for echoes to come back to us. And when we listen for echoes, different tissues in the brain reflects this signal or absorbs the signal differently. So we get back different tissues gives us different contrast, and it creates it appears different contrasting to different tissues. In this particular slide, I'm showing a T2 weighted protocol where the this energy pulse is known as the RF pulse or radio frequency pulse is applied in a particular fashion or in a particular uh, way, and we expect our signal to come back. So no diffusion sensitivity is applied in this particular protocol, and this contrast is used for reference. This particular contrast represents free water density in different brain tissues. Now, in the second step, we introduce this particular diffusion time and diffusion gradient. And we introduce diffusion gradient and we apply that at a particular diffusion time. Now, a diffusion MR protocol is controlled by two things. The first one is a B value, which is a conjugate term of this diffusion time and diffusion gradient. And the second one is the B vector, or the directional diffusion sensitive gradient. A bit more about the B value. So we see that previously the diffusion length had a relationship with diffusion time. We see the same thing, same relationship for the B value. in the cases of restricted diffusion in different cases. So, and this is expected because b value is a term which comprises of diffusion time. Now, when we look at the diffusion signal, we see that this diffusion signal is inversely proportional to the diffusion length. So this relationship that we see, it's actually inverted, whether it be linear or restricted cases, where it is nonlinear. And for the B vectors, you can see that for the same region, for different directions, we are going to have different signals. What that essentially means is whenever the gradient direction of diffusion sensitivity is parallel to any fiber, any tissue fiber in the brain, what happens is the spins get to move. And when the spin moves, there will be spin dephasing and we will lose signal. So that will create some blackish region in the contrast. And whenever these B vectors are perpendicular to a particular fiber, then the spins are restricted at a particular region, so they cannot move, and we retain that signal. So that appears as white in these images. And finally, when we have sampled the whole sphere, we can use different mathematical tools or different mathematical functions to represent that signal on the spherical space. We could use 2D tensors or spherical harmonic basis functions to represent them. One of the examples of this particular approach is DTI, or diffusion tensor imaging. And so these functions actually can express the signal in different ways. But in terms of the brain, if we look at the brain, we will see that there are different components that are there in the brain tissue that contributes in the diffusion signal that we receive from the scanner. And there can be intraaxonal space, extraaxonal space, and CSF water. So these different waters are restricted in different forms in the brain. And so we can take the fractions of these compartments and combine the diffusion signal they actually represent, and finally represent the diffusion signal that we receive from the scanner. These are biologically motivated models, so these are known as biophysical representation. But one problem with these kinds of approaches, we need more information to represent different compartments. So we need to sample different B values, and this needs to be done on all over the sphere. So the samplings are done on all over the sphere in different directions of diffusion sensitivity and with different B values. So as these actually look like shells, when we combine these two together in our diffusion protocol, this is known as a diffusion multishell diffusion protocol. This brings us to our problem statement. So in the clinical diffusion MRI, we see that this number of samplings on the Q space, this is substantially reduced. And also in the clinical diffusion MRI, to solve for multi-compartments, biophysical models requires multi-shell data, but in clinical diffusion MRI, that's not available. So we have to rely on single shell data to solve for multi-compartments. And that brings us to our hypothesis, which states that to recover that we can actually recover the lost microstructural details arising from these problems from the limited Q-space resolution in the single shell protocols with DTI and NODDI by leveraging AI. Now let's look at the problem in a deeper way. So we were suggesting that as we reduce the number of directions, the data quality, there will be loss in information. And so as we can see in the form of SNR here, as we reduce the number of directions, there is essentially difference in the SNR and we are losing signals. This is true for the DTI-based FA and also DTI-based mean diffusivity values. I will shortly explain what these metrics are, but this brings us to our specific aim 1, which is to improve the angular resolution using a reliable ML feature that can recover clinical information loss. Now, a bit background about the diffusion tensor imaging. So for this kinds of model, we basically solve this equation right here. From the scanner, we already know the diffusion signal S. We already collected the S0 reference image in the first step, and uh, we already know the B value and this G vector from our protocol. And we are essentially solving for this D matrix. And when we have this D matrix by using weighted least square method, we can essentially decompose this into its principal eigenvalues and eigenvectors. So when we have already three largest eigenvalues, we can represent that as a 3D ellipsoid that can explain our fibers in the brain tissue. So the eigenvectors can be represented with the fractional anisotropy like this, and this represents the directions of the fibers. And we can use these lambda values, these eigenvalues, to actually form different scalars. So the average of them gives us mean diffusivity, or the uh, last two radial diffusivity is given by lambda 2 and lambda 3, and the axial diffusivity is the principal eigenvalue that we have. And these maps are shown over here. So what we are saying is that DTI with lower angular sampling results in clinical information loss. Now, what do I mean by clinical information loss? So for this particular slide, we had 50 episodic subjects, episodic migraine patients, and 50 chronic migraine patients. And their differences were taken in terms of axial diffusivity on a white matter skeleton shown in blue here. And the significant differences for 61 direction is being shown with red here. And also, you can see that there are many red regions with 61 directions. But with 21 directions, the red regions are reducing. So we see very less red regions. So these clinical differences are not really seen. And we are saying that reducing the number of direction is losing this information, these clinical differences. And this is what we are defining as clinical information loss. So one way to solve for this is to use diffusion signal interpolation on the Q space. We could use Delaunay triangulation on the Q space to basically get the edges and the vertices. And from there, we could calculate the distances on the spherical triangle, and we could try to get our coefficients and try to solve for the signal at different spherical nodes. But one problem with this approach is the generalizability, and also this does not account for clinical information loss. Now, to make the solution more generalizable, it is advisable to use machine learning or deep learning framework. And to apply any kinds of machine learning or deep learning framework, we have to go through these steps in this flowchart. At first, we have our data set. From the data set, we clean our data. And then the most important part comes in, which is feature engineering. In the feature engineering, we actually decide that what should be used from the data to learn. And when we have decided what we want to learn from the data and decided on different features of it, we can select different models that can help us in the learning process. Now, different kinds of models like these jargons or these acronyms, they are actually specialized in handling different kinds of features. So depending on what kind of features we have chosen, it will determine what kinds of model we are going to be using. And when the model selection is done, we are going to use any kinds of learning algorithm or optimizers to optimize our model. And finally, some new data set will be used, and based on clinical evaluation, we can evaluate our trained model. In general, the clinical data sets like diffusion MRI should use clinical evaluations, but in general, till now, the practice is to use visual or MSE loss for evaluation. Now, to apply machine learning on diffusion signal and to do feature engineering on it, we need to understand the diffusion data. So diffusion data can be represented in different forms. Our diffusion signal can be represented as a sparse representation on the Q space that keeps the angular and the geometrical positions of the nodes. And we can represent this as a spatial case, like stack of 2D, 3D, or 4D images. Or we could just say that we have one voxel and we could take 1D diffusion signal based on the protocol from the Q space. One thing we noticed is that when we selected our feature, these different kinds of models will come into play, and we can use these specialized methods to handle this specific type of features. One important thing that we note is that the geometrical context is actually lost in the spatial and sequential representation. And there's this shortcoming of spatial reconstruction with AI, where we see that there's a chance of hallucination with the unit or CNN type of structures, which is problematic in the clinical cases. The hallucinations can introduce different new structures, which is all not there in the patient. So this is problematic. And you can see that based on unit reconstruction from this particular image, we observed that the hallucination maps occurring in the out of distribution data, as well as in the in distribution reconstructions as well. And this is very much problematic for the clinical data sets like diffusion MRI. So this brings us to our updated hypothesis, where we are saying that using an MLP with geometrical features on the Q space, we will be able to recover the lost clinical information from the limited clinical diffusion MRI reliably. And so we defined our fully connected network, which is a very simple network with 2400 learnable parameters. We sampled our data set from a patch-based approach. We used 3 subjects for training ROIs and 5 subjects to get the validation ROIs. And this is what our schematic diagram looks like. So the node we are estimating for, we take the neighboring nodes that are known with their signal values, and we do this for all the 27 different neighboring voxels. And we actually format them in a 27/3 fashion and train it with our fully connected network. And our training follows 3 training phases. And these 3 phases include the stochastic gradient descent method, which gives us a very initial rough and fast convergence. Then we fine-tune our model with Adam algorithm. And then finally, we further fine-tune it with the RMS prop algorithm. Now, this is what our visual result looks like. For now, let's focus on the 61 and 21 gradient direction results for FA and NODDI. You will see that for 61 and 21 directions, the differences between these 2 kinds of maps visually, it's very hard to differentiate anything between them. Also, for different reconstructed results by using any of these approaches, any of the deep learning approaches, it's very hard to distinguish them. And our structural similarity index values and PKSNR values actually gives a quantitative evaluation or validation on this similarity. So how do we understand if there is any clinical differences or not, or any clinical information is getting lost in the process? To evaluate that into our model in our scoring system, we use 2 performance matrix. One is the tract-based skeleton score system. Another one is the JHU-based ROI scoring system. In both the scoring systems, we penalized with false positive and the false negative rates of the different reconstruction techniques using data-driven approaches. And we took the sum of the mean. We took the mean of the FA, AD, and MD scalars from the DTI. And the total score was combined in this way, which gives us our global matrix. Now, before showing the final result, I just wanted to highlight this false positive and true positive rates of different representations of the diffusion data, clinical diffusion data. So the spatial representation actually had more false positives, as evident in here, than the sequential and the sparse representation. And finally, so this particular work was part of a MICAI challenge in 2022, and our work actually obtained the highest score. And we showed that we were able to get 21.3% unique information from the dataset, limited clinical dataset that was given to us. And the dataset, so the complete validation ground truth data was not available to us when we sent it to our collaborators, so they evaluated the final score for this particular slide. Finally, when we look at our training resource requirements, we see that our approach achieved using minimum training resources compared to different other techniques in the field. And this is important for clinical data sets because in clinical cases, the data sets are pretty scarce, and to train our model, we actually need to apply our model on so many testing data sets. So it is important that minimum training resources are used to train these kinds of models. So in summary, we proposed a Q-space geometric prior that helped in upsampling the diffusion weighted image data by keeping the clinical state-of-the-art clinical context. The model features were rotation invariant, so which meant that we needed lower resources to train our model, and the computation was easier and suitable for clinical diffusion MRI. The limitation with this kinds of approach was that it could only be applied on the optimized Q-space protocols and did not account for biophysical models. Now, since we accounted for the first problem and own MICAI challenge in the process, this brings us to our second problem, which is to try to solve the multi-compartments just by using single shell data that is available with clinical diffusion MRI. Now, before going into the problem, I would like to give you some background about the biophysical model that we are using for this problem, which is NODDI, or New Right Orientation, Dispersion, and Density Imaging, where we see that each voxel that we get the diffusion signal from is actually majorly divided into two compartments. The first one is the free water, and another part is the complementary part of it, where the new right component of the cell resides. So the new right component restricts the water in a harmonious fashion, like it is going in different directions as the fiber goes. And there are also some water, extracellular water, that is outside the neurites and that hinders these different neurite compartments. And so the signals actually is modeled based on these three compartments, and we have the fractions of these components defined as well. So basically, two important parameters are the neurite density index, which is also known as the intracellular volume fraction. Another is the free water or isotropic volume fraction. Another important parameter for this model is the orientation dispersion index, where the orientation dispersion index defines the geometry of the problem. And this ODI, as you can see, the neurite density could be higher or lower, but the ODI will remain the same based on the dispersion of these neurites. So in summary, this NODDI model is actually trying to model these three compartments, intracellular, extracellular, and free water, and combine their different fractions to give us our final diffusion signal. And these different compartments have some intrinsic diffusivity constants defined with them, which is in general for standing free water it's 3.0, and for intracellular water 1.7, and for extracellular water it's related to the D parallel here. And we actually optimize our signal based on this function over here. So basically this function has two primary variables. One is A, that the signal that we just modeled with NODDI, and another is the M, which is a machine-derived signal. Now what this function actually spews out is a value that tells us how similar these two signals are. So we basically optimize this model based on this particular function, Riccian log likelihood function, defined like this. Now, the problem states is that single shell diffusion cannot resolve multi-compartments, and this is evident from when we tried to fit this NODDI model using single shell data. Here the protocol used was P1, P2, P3, which was around 1000 B value of 1000, 2000, and 3000 used here. And we see if we used multi-shell diffusion data, then our result looked more coherent. I'm not describing the color map here, which I will do very shortly, but what I'm trying to show here is that the single shell results are not really coherent. And this brings us to our specific aim 2, which is to find the conditioning parameter that stabilize the single shell NODDI problem within the simulation. Our hypothesis was that if we could condition the NDI, ODI, or free water, either of these parameters, this can stabilize the ELPOS single shell NODDI problem. So we took a high quality data set from Human Connectome project, took some healthy brain, and when we represented those parameters in a Gaussian manner, we represented them in 3D Gaussian manner here. It looked something like this. And this inspired us to define our parameter ranges based on that particular distribution. So our NDI, free water, and ODI was selected based on those ranges. And we had also 2 additional parameters of axon radius and different fiber directions. Combination of these parameters gave us around 100,000 cases per protocol. And the protocol that we used was the 7 protocols, and 3 of them was single shell with 90 directions. B value of 1000, 2000, and 3000 was used in the process. And so this is the visualization or the spherical harmonic basis representation of our simulated data, diffusion data. And in our conditioning experiment, we saw that when the NDI and ODI parameter was conditioned with single shell data, the result was not close to the ground truth. But when we conditioned the free water with single shell data, our result was very close to the ground truth, and that was a promising finding. We saw the same thing happening with the with the in vivo data when we used multi-shell derived free water as a prior with single shell in NODDI problem. We saw that we could retrieve the NDI and ODI in the problem. And this meant that if we had this free water information somehow, we could actually use the single shell data to derive NDI and ODI values. So we looked into the literature, what type of data-driven approaches that could be used to estimate this free water parameter. We came into this model like MEDN, which was microstructure estimation deep network, and the extension of that model, PMEDN, which was performing really great in estimating these 3 parameters. But the only catch was that they were using multi-shell data. So we wanted to know what would happen if we used single shell data. And this is what the results look like with single shell data with that kinds of model. We saw that single shell free water was far off from the simulation ground truth, so it did not take us anywhere. But we were observing that in simulation, the data-driven approaches were very, very close to the ground truth, and the original NODDI model, it was overestimating the free water parameter in simulation. So in aim2 summary, we see that the conditioning of this free water parameter actually gave us single shell NODDI reconstruction, but the limitation was that we could not get free water parameter independently by just using end-to-end AI, which limited our single shell NODDI estimation. Which brings us to our specific aim 3, which is to solve for single shell estimation of free water using multimodal MR priors, and clinically finally validate whatever single shell outcome we have from the NODDI. To estimate our hypothesis was that to estimate free water parameter independently, we would need multimodal MR priors that can sustain tissue water contrast. So with our model, we introduced two priors. One is the mean diffusivity from DTI and the S0 image that is already available from the any diffusion protocol. And when we included these two into our model and followed the same simulation, this was the result. If we zoomed in, we can see that all three methods converged in the multishell data. So all the three results converged in the multishell data, and the only with the ones that used the prior, shown in blue here, was very close to the ground truth values. And so we compared our method. We compared our method with different free water estimators in the field in the same simulation. So what we did here was we used four different approaches. In four different approaches, we had two of the approaches that were data-driven, and two of the approaches was not data-driven. In the data-driven techniques, so for the non-data-driven techniques, we saw that. Oh, I'm sorry about this. Kimku, Asho. Sorry about that. Okay, so we had four different methods here. So four different free water techniques were there. Among them, we had two data-driven techniques and two non-data-driven techniques. And for two non-data-driven techniques that we had was DTI-based free water and the NODDI, shown in purple and red here. We saw that in multishell, they were overestimating free water, and in the single shell, they were not even close to the ground truth. But for the data-driven techniques, we saw that in single shell, they were very close to the ground truth, but with p-medon, or extension of medon plus, it was giving us very high variance. But in our case, the yellow triangular results actually had lower variance and very close to the ground truth, where we were using these priors. And we saw the same thing happening in the in vivo results. So now let me describe the color map a little bit. So the different colors that you see in these maps represent the water component or free water component in the brain. And the ODI is represented with the saturation values. So ODI represents orientation dispersion, and the intensity value is representing this neurite density. And so you can see that with single shell cases, our result was coming with coherence, which was not possible with the original NODDI model. Although we saw some differences between when we were using different B values between these maps. So we compared our result by using a very high quality HCP dataset, Human Connectome Project dataset, and a clinical dataset, which is a cerebral small vessel disease dataset. So using single shell, we saw that our result was getting a very high SNR. And this was not only because we were using deep learners, which generalizes the results generally, but it was also because our priors were very high, with very high SNR values. So for any diffusion protocol, we will have these S0 images that will include high SNR data priors. And so we can use them with our high gradient values data. So as we increase our gradient, you can see as we increase the B value in the protocols, the SNR decreases. This is also true for the clinical data. I want to highlight this drastic difference between the high quality HCP data, which had B value SNR, B0 SNR as 450, and the clinical data, which was around 20. And for the P2 protocol, we were almost losing all the signals, and there was more noise here. So you can imagine how multishell fitting could actually impact the fitting quality. So then we took one of the cases from this CSVD study, which was a white matter hyperintensity case, that had a lesion volume of 3 centimeter cubed. And we took a slice of it, and I'm showing the free water single shell and multi-shell maps here. You can see that the SNR drastically improved, as well as the CNR. This was also true for the neurite density maps. We saw the SNR and the CNR improve. And this brings us to another important slide where we are comparing the objective value histograms. And these objective value histograms was actually based on the distribution of these likelihood values obtained from this function. Again, just a reminder, this function basically takes two things. One is the signal that we modeled using NODDI, using our parameters, and then another value m is the machine derived signal, diffusion signal that we receive. And when we put this in this function, it gives us L, which is a likelihood value that tells us how similar these two signals are. The similar they are, the better our modeling is. So when we do this for the whole brain, when we feed our diffusion signal for the whole brain, and we get the distribution for the whole brain, this L distribution, we can represent them like this. And we did this for different protocols. As you can see, that for the single-shelled protocols, they were actually residing at the right side of this x-axis, and it was skewed to the right compared to the multi-shell data. So especially for P1, and if you look at the red one and the blue one with NODDI P all, which is the multi-shell data, you will see that the multi-shell distribution was at the left. So for the high quality data set, these distributions was very close to each other. That meant that our fitting quality was not that much degraded with the multi-shell data. But when we looked at the clinical data set, we saw that the multi-shell distribution, it was far left from the single shell distribution we had. The mean values were drastically different between these two distributions. And so from here, we can actually say that our optimization with single shell protocol, it was actually getting us to a better hyperparameter space. This brings us to our clinical validation by using some physiological processes like aging. Now, for this validation strategy, we had around 64 subjects ranging from 20 to 70 years old. And from literature, we already knew that the neurite density lowers in the gray matter with aging, and the free water content can actually get higher with any neuroinflammatory process going on in the brain. So we looked at the gray matter and the white matter portion of the brain, and we observed that the free water was increasing drastically when we were using P1, P2, or the multi-shell protocol. So for all the cases, we saw the same trend happening. But with the multi-shelled case, with white matter, we saw the significance value was actually off. But with single-shelled cases, our sensitivity was much better. Also, when we observed the ODI and the NDI parameter, we observed that the ODI parameter never changed with significance by using single-shelled P1, P2 or the multi-shelled P-all protocol. But what we observed with NDI was that the gray matter sensitivity was being hampered drastically using high B-value single-shell data or the multi-shell data. So the NDI was reducing with aging, and that is what we observed from the literature. We saw another case for the cognitive scores where we had two groups in hand. One was the HIV positive group shown in red here. Another one was the control group shown in blue. So when you look at these two different groups, we also saw similar kinds of trends coming in. For ODI, or orientation density parameter, the significant levels between these protocols did not change, and the trend was the very same. But for NDI, we again observed that the gray matter with P1, it was actually following a significant trend for this HIV positive group. that trend was getting lost with other two protocols here. Then finally, we finally performed the correlation between the NODDI parameters derived from the single shell and the multi-shell data. For this, we used Johns Hopkins Atlas for white matter tracts, and the Harvard-Oxford Atlas for the gray matter cortical and subcortical region. And the results looked something like this. For all the cases, we had very good correlation, which is always good to see. But we observed that for the gray matters, they were sensitive to single shell NDI, and they were changing a little bit from that correlation. And from the previous slides, we already observed that the objective histogram and aging and the cognitive validation for P1 protocol already showed and concluded that we were getting some sensitivity and reliable significant trend with NDI when we used this single shell P1 protocol. So that actually helps us conclude that the gray matter changes were more sensitive to the single shell NDI. In summary, we proposed an approach that stabilized. So our approach actually stabilized and improved the results in terms of objective value SNRs with the single shell data. And our proposed approach was validated using clinical white matter hyperintensity, aging, and the cognitive cases. And finally, we also showed that the gray matter was sensitive to single shell NDI. The limitation with our approach was that the number of B vectors we used in the clinical CSVD data, it was around 64, which is generally higher than the general clinical diffusion MRI data. So in conclusion, we used this limited Q-space resolution and single shell clinical diffusion MRI data to upsample the Q-space, and we won a MICAI challenge in the process. For the second aim, we explored and conditioned the ill-post single shell NODDI problem in the brain microstructure simulation. And for the third aim, we applied multimodal priors to solve the ill-post problem in NODDI and perform the clinical validation. To address the single shell estimation with very limited Q-space resolution, we can actually combine the aim1 and aim3, which we hope to address in the future. And for aim1, we already know that this applied only for the optimized protocols. So to address the unoptimized protocols, we needed to incorporate zonal features, and we can do this by actually, so we already did this and we have some of the results from this future work. We hope to publish something very soon. With that, I would like to conclude my presentation, and before moving on to any questions, I'm grateful to God for finally I'm here and the opportunity to benefit from the facilities of EOFR. I would like to acknowledge my wife and my family before anything else, and this goes without saying that without Nasir, Giovanni, and Marvin, I wouldn't be here. So thank you for supporting me at every step of my research works. I have to say, people generally get one. I have had the chance to work with two wonderful groups, one in the neurology and another in ACE. And I would also like to thank Professor Jianhui Zhang and Professor Santiago from the MICAI Challenge organizers. There are so many people I would like to thank, some from my community who helped in the proofreadings, to some actually discussing ideas and help in learning. It will be hard to mention all the names, but I want to let you know, if you're watching, your help meant a lot to me. And thank you. As you can see, I have a problem for every solution, and it's not really over. There's a long way to go. But for now, I'm ready to defend any questions you have.